introduction. It's a pleasure to be with you all here this morning. Um, I'm not an oral person, so I don't know if it makes me an outlier or at least a close cousin. But I've been working in the area of adaptive control, as Deb alluded to, as an introduction for more than 40 years. This topic is something that is very near and dear to my heart. And I could talk about this topic for hours until the cows come home, as they say. And I would still have only barely scratched the surface. So it is a pleasure for me um, to convey some of the highlights of this topic and what I see as the potential intersections between learning, and it's deliberate that the reinforcement is not there. So it is what I want to make really is a connection with what we think of as learning in the context of dynamic systems, and maybe provide some hooks to some of the things that may be familiar with you, most of whom I'm assuming are leaders and pioneers in RL and know a lot more about it than I do. And I'm hoping for some dialogue as we go along. So the work that I'm reporting here is something that my collaborators and students did, and I'm merely the spokesperson here, and I've been along for the ride, so to speak. But it's pleasure for me to do that. And Peter, Johannes, Anubhav, Joey, Heather, and my collaborators, Eugene and Mike at Boeing and A4L, have participated in the research that I'm going to talk about. So this is roughly the outline. So the point that the where we get really started with this whole thing is in the context of actual physical systems, engineered systems that we're trying to control. So this is a sort of a standard representation of how things proceed in a dynamic system. So these elements that are in here are airplanes and robots and self-driving cars and motors, precision machine systems, machine tools, things of that sort that need to be somehow designed so as to meet some system goals. So, and the idea in many of these things is that there is an external agency, some sort of an outside influence that we can have that allows the system property to change, and that basically is what is represented in here. And typically, the way these systems are designed is that there's a whole bunch of timescales involved. And so what you think of as inner loop are things that are faster, so that things are regulated quickly. And outer loop is a slower timescale, like planning a particular path or overall set points saying, go there, come here, and that sort of thing. So this is typically how the design proceeds. And we always worry about making sure that we can meet those system goals in a stable manner. So meaning that if you kick it, things die away and not really grow and have this sort of positive feedback effect, which we don't want. We don't want any resonances. We don't want oscillations. We don't want divergence. We want things to be well behaved. So that's sort of a mantra, if you will, that I'll keep returning to often. We want to make sure that anything that you design with these systems, you want to always have some sort of guarantees that if there are some perturbations, then those die down. We worry about safety. It's not just meeting the system goals. There are other things that you need to make sure do not get violated. Don't hit that obstacle. Don't run into the pedestrian. Don't enter the stall region, and so on and so forth. So we always worry about safety. And of course, wherever you can, the primer of all of these things is that don't waste too much money. Do it in minimum time with minimum energy, minimal cost, maximal whatever the performance might be. So these are very typical goals that are looked at and controlled. So, and always in all of those things, nothing is certain. All models are wrong, and some models are useful, is really what is often said. And so you have to, no airplane is really going to be a perfectly behaved dynamic system. You have a model, but there's always going to be things that cannot be modeled or very difficult to model. And even if you do, doesn't necessarily tell you that you know how to design the real-time control. So all of these things have to be kept in mind as we go along. And this area and you have to meet constraints. You have to really stay within certain limits. The temperature cannot exceed a certain value. The current cannot go beyond a certain, et cetera, et cetera. So, and this has a very long history. In fact, we can trace it all the way to the water clocks of the Greeks and the Chinese. And in fact, I heard a talk recently about how James Watt basically was fundamentally responsible for the Industrial Revolution. And it so happened that some key individuals met. And because of that confluence is when this engineering marvel, which really relies, is a substrate for all of the power grids that, the electricity that you and I get. And so that he too, again, designed one of the first feedback control systems that sort of sets the stage for having this become sort of a systematic engineering discipline. And since then, there has been a whole bunch of applications, aerospace, process control, to just name a few. And these are some of the success stories that we actually were put together in this report to, not just physical systems, but cyber physical systems, meaning that there is more and more of a need to monitor these things, sense them, communicate the information through a variety of communication layers and devices, and of course, do the computation as quickly as possible and actuate it so that you can indeed design the real-time control. So it's really a nexus of the cyber and the physical worlds. And it's not just something that only is for the specific engineering systems. It's things that we can actually take up to the grand scale of really societal challenges. So if you're really dealing with climate change, what are some of the fundamental principles that tell you how you can improve the performance of the system and move towards a decarbonized world? How do you deal with systems biologies and not just understand what happens and come up with a descriptive solution, but a prescriptive design where you could see if you can nudge those stem cells in order for your systems the biological systems to be better designed. If we have this big push towards electrification, where not only just power, which is generated, is really coming from wind and solar, but also transportation moving towards an electric propulsion, a lot of the industrial processes becoming more electrified. All of those things really lead, again, to grand challenges at the societal level. And how do you design smart cities and smart grids and smart infrastructures by paying attention to this nexus between the physical and the cyber world and figuring out where you have fundamental physical mechanisms that tell you how to model it, and where data that you get is something that you can combine with that is really what the field is about. So in all of these things, now that's a very broad topic. I'm not going to talk about all of that, but just specifically the ones that involve adaptation. So the question is, what is adaptation? Now, now that you have a sense of what we're talking about in terms of real-time control, and let's say that you have this box and this box here, and for some reason we call it a plant, which I think the origin of that came from process control. So this is processing plant, like cement and glass and paper and so on. So what this is the actual real world, the physical system that you're trying to control. And these are the control inputs, and the actuators are the ones that take the data into an energetic value that is of relevance. So for instance, this could be voltage, or this could be heat, or this could be a control surface deflection. All of those are inputs that basically have some agency into monitoring and directing and improving potentially the performance of this. So when you have a system like this, in real time, you've got some uncertainty, stuff breaks, things age, and you've got some sort of a malfunction in your actuators. So when that happens, you want to basically have this signal step up and learn implicitly or explicitly that something has gone wrong and direct the performance in real time. That basically is what we are interested in the context of adaptive control. So how do you have this cyber layer figure out on the fly in real time what you need to do, what you need to change so that you're able to accommodate these anomalies and still have the system meet goals. So that's the name of the game in here. So the basics of this basically is all about provably correct algorithms. And what are you trying to learn? So something went wrong, right? So that's what I'm calling as a parameter. And this is where some of the elements, you can probably see when you parameterize a Q-learning using neural networks, the weights could be these parameters. So these parameters, but here, in the context of what I'm talking about, this theta is a physical quantity. Like, for instance, what's the effectiveness of how what the actuators provide to an airplane that allows the airplane to turn, to maneuver. So if that is something that is uncertain because you've got some kind of a loss of effectiveness in the actuator, then that's what you're trying to learn in real time. But at the same time, you're also trying to figure out how to deflect those surfaces in a way so that you're able to improve the performance. So that really is what adaptive control is trying to do. It's trying to learn, and don't worry about the details of why it is specified as a differential equation. It's just for analytical tractability. And how do you design the control input, which could be, for instance, a force or a torque or a heat and all that, like I mentioned to you. And how do you do these things so that with some sort of guarantees? That really is what adaptive control is all about. And that adaptive control, too, just like control systems, has a history of about more than 60, 70 years. So in all of these things, and here is where maybe there are more parallels that begin to emerge between RL and adaptive control. There are two kinds of errors that we always contend with. One is like, for instance, a loss function type of thing. And that is what we call in here as a performance error. So E squared, or some kind of a positive definite function of E. The other is where you need to be. So for instance, if you're training the weights, where the weights need to go to, minus what you have in here. So that's a parameter error. So this is what you can measure, and you need to reduce it, and this is what you can adjust, but you don't know what it should be. So this is the learning rule. And so how do you then design the rules for adjusting the parameter so that this performance error goes to zero? So this too, you can see, brings in some parallels to the kinds of things that you worry about in the context of, say, back propagation error. So how do you determine the error model, the one that basically relates the parameter error to the performance error, and the rule for adjusting this parameter is really what it's all about, right? So if you take a very simple linear regression problem, again, something that is quite familiar to you. If you take a linear neural network, that really is what it is. So let's assume that that's really your system model. So phi is basically some underlying regressor that basically determines the system. So with that, you basically build an estimator that looks like this, because you have reason to, you kind of use what is known as a certainty equivalence idea. So there is a performance error and there is a parameter error. So you use that. In this particular case, it turns out that the two quantities that I talked about, the parameter error and the performance error, are really related by a very simple linear regression equation. And so because of that, you could simply take, and I've built a very simple example in here, obviously. So you could just take something like E squared. And it turns out that in this particular case, it is indeed a function that looks like this, except for the degenerate case where the regressor is orthogonal, in which case it becomes flat. But still, it's something that where if you use a simplest gradient descent, you can indeed converge to zero, and that's great, and that's exactly what we would like to do as well. And so in many problems, it turns out that you can take the underlying complex physical system and the control design and collapse it to this very elegant structure, and we can show that indeed that's something that gives you what you're looking for. So in fact, we called it error model 1 in some of the things that we've done. But, and here is really, again, where there is a departure. You can't always do this in a dynamic system. You can't always rely on back propagation and the gradient type of things, and sometimes it's just the wrong thing to do. And that is something that is really comes from dynamic systems, and because of lags between what you can adjust and what you're really trying to effect. So it turns out that you don't always have the access to this signal, but you really only have access to whatever you're interested in after a lag. So think of this as a dynamic operator. And the dynamic operator is there because physical systems have inertia, they have capacitance, they have stored energy, and so it takes some time for them to respond to whatever inputs that you give. And because of that, if you take something like E squared and you use the gradient algorithm, it really is not a good idea when you have this dynamics. And it turns out that this is something that people have looked at and articulated a long time ago. And a better choice is really this quantity. But unfortunately, you don't have access to this quantity. It's something that is internal to the system. And therefore, it turns out that you really can't use this gradient rule. So this is a big departure and something that potentially distinguishes what we've been doing in adaptive control. And it's so the way in which this bottleneck, the hurdle was overcome is by pivoting to what we call as a Lyapunov method. And the Lyapunov method basically says, no, don't try to just minimize E squared because that's going to give you trouble. So look at a different quantity. And it turns out that in some cases, even if you use a very simple thing, rule like taking the performance error and correlating it with the data, which is not, remember, phi is not the gradient of this quantity. So this is not E phi. So that's the main thing. So even though it's not the gradient, it turns out that you can actually show that there is some positive definite function that is going to be non-increasing, and that gives you basically the analytical basis for making sure that everything works okay. So that is really the one that underlies all of adaptive control. So if you go back to this problem in here that I mentioned, instead of thinking of it as a gradient rule, because it might not quite look like this, what you try to do is to use a stability framework, which is a different way of looking at the problem. And it turns out in this simple case, the two coincide, and it gives you a non-increasing positive definite function, and then you continue go from there on. So, by the way, at any point, please do stop me if you have any questions, and we would love to make this a very interactive hour. So you can take the same idea now. I mean, nothing is going to be a linear regression. Nothing is going to be in low dimensions. And so you do need to worry about the scenario where you have multiple states. And all of this is essentially saying even when you increase the order of the system, you can still have a rule of how do you adjust a vector of parameters. And you can still look at something like a positive definite function, and you can still show that everything is well behaved. And you can rely on some real analysis arguments of continuity, differentiability, and well-behaved norms in order to show that the error goes to 0. So, and you can also look at like the equivalent of POMDP. So you only have partially observable systems. And so you only have, for instance, there are multiple states. This is, again, a dynamic operator in here. And so you have a lot of states hidden in the system, but you can only measure a part of them. So you then come up with some kind of an observer, which also doubles as a controller. And you basically, these are filters that generate these states, which end up being actually estimates of the actual state. And because these converge very quickly to the actual states, you're able to get a nice, stable adaptive control architecture that tells you how to go about learning how to go about determining an adaptive control input. I'll come to learning a little bit later. Okay, so that again gives you stability. So you can see, as I mentioned before, the focus is on stability because you want to make sure that when you are making these real-time changes and trying to figure out what the actual parameters are, you want to make sure that nothing runs away and you have a stable foundation, so we worry about stability. The other departure, which you, I'm sure, have noticed here, the treatment of everything that I'm talking about is deterministic. It's not stochastic. We haven't really brought in any kind of stochastic random components. But that doesn't mean that this is only restricted to deterministic systems. But the stochasticity, the way in which many of these models proceed is that they're relegated to, say, measurements. So if you have measurement noise, then that brings in stochasticity. There could be disturbances, wind gusts, and so on. And that is looked at as a stochastic problem. And the other thing that you would have noticed is the treatment here is in continuous time, because these are analog quantities. A robot has a position and a velocity at every instant of time. The world doesn't progress in discrete chunks, so it's an analog world. And so continuous time descriptions of these systems are a more natural vehicle, and a lot of these things do proceed in continuous time. That doesn't mean that we cannot do all of these things in discrete time. There's a whole discrete time systems analysis, Lyapunov functions for discrete time, adaptive control for discrete time, all that exists, but I'm just not going into that right now. But you can see, you can infer that there are indeed many of these parallels. Everything that I've talked about so far has looked at linear dynamic systems. Nothing in this world is linear. It's always going to be non-linear. And so if you now have a known nonlinear system, then you can sort of make some headway if you know something about these nonlinearities. Like, for instance, in all of the problems, what you're looking at is a description of a physical system. Again, to come back to an airplane type of story, we know many of the underlying mechanisms that contribute to the motion of an airplane. So when you deflect a control surface or when you introduce a thrust, then how that actually manifests itself in the form of a motion is really determined by the underlying inertial components, which, so gravity, and there is fundamental equations of motion that comes from Newton's laws, and then there is aerodynamics. And a lot of these mechanisms are things that one can study and model, and so underlying constitutive equations and constitutive relations and conservation equations give you a lot of insight into how these things move. So it's not that F and G here are totally unknown, and so, but there is a model. So the structure of the model is known, but the parameters of that model might vary. That basically is the way in which we proceed with these things. So with that kind of a structure, we can do feedback linearization, and then adaptive nonlinear control goes about saying, hey, I happen to know that this is a kind of structure that I have. I have some sinusoidal nonlinearities, quadratic nonlinearities, because that's the nature of the physical mechanism. So you use that information, but I don't know quite exactly what some of those physical constants are, because they represent the constitutive relation, and with age and time and temperature and environment, that can change. So you go about estimating those parameters, and it turns out that in many cases, you can indeed find suitable functions. It does require knowledge of phi, and that, again, what I'm saying is really something that comes from the physics of the problem. But again, to do the mapping between that and a neural network, if you assume that this particular example, you can think of it as a single linear network where there is no activation function. And so once again, the elements that you introduce in here are things that you can utilize in order to say make some analytical conclusions about linear networks. And there are many papers in the literature that do that. Okay, so I've given you, I hope, some kind of an idea of what the foundations are, which basically determine the theory of adaptive control. So what's all this good for? So here is an example of what we were able to do, which is a practical illustration of adaptive controller. So in this particular case, I'm controlling a drone, and the drone is, the video is that's what it'll show. And I remember I told you about in real time, things can go wrong. And so online, on the fly, you have to make your adjustments. So here in this quadrotor, so there are 4 motors, right? And there is a propeller. So what if, as the quadrotor is hovering, the propeller blade breaks midstream? It doesn't break so much that you lose control altogether. So there's some control yet. The actual amount of control is basically compromised. So that's the video that you'll see. And what you will see is that there are 2 kinds of demonstrations. One where there is no adaptation, and one there is adaptation. And as you can imagine, that you will see what the difference is. I don't think there's sound, but that's okay. So the one with the white blade, white is the one that the propeller broke. And so you can see, obviously, that there is a roll disturbance, and then it crashed. So here, this is with adaptation. So you can see that it basically readjusts itself and does fine. And the way in which we simulated a real-time anomaly is that we had the propeller blade made out of graphite, and we actually cut it. We stuck it together with duct tape, and there is a little razor blade that is in here. It pops up as the propeller is spinning, so it cuts the duct tape. So in real time, it basically reduces the momentum. So that's what we tried to do. So we don't really work on drones in our lab, but our goal was really trying to establish what adaptation can do. And so this was the simplest experiment that we could think of that basically emulated a real-time uncertainty in mid-flight. And that's what Zach was actually very clever at and was able to show that it works. So that's the kind of thing that which illustrates that you can do. There's a lot more videos, but I didn't really bring all of that in here. So that gives you that, yes, an idea that these are hardware demonstrations of the concept. So now the next thing here is that there is a lot of uncertainties beyond parametric uncertainties that can happen. And so we basically introduce other kinds of anomalies, like uncertainties in terms of not just parameters, but also input saturation uncertainties, unknown actuator dynamics, unmodeled dynamics. And in all of these cases, we can show that by using notions of regularization, which is, again, a tool that is used in RL, we can actually provide some guarantees. Projection, which is, again, a notion which is a commonality. Sometimes we also look at the notion of a dead zone, which is that when you are uncertain and when your magnitudes are of a sufficient quantity, you don't know whether it's due to noise or due to actual data, so don't even do any kind of adaptation. So that's the dead zone idea. So we want to also look at another kind of constraint, another kind of property that's always present in a dynamic system, and that is input saturation. So you have a limit on the control authority as to how much force that you can put in, how much torque, et cetera. And so we wanted to make sure that indeed we can carry out our adaptation even when there is input saturation. And so what we did was to really show that in many cases, you can model the effect of saturation as an additive disturbance. And by modifying the performance error suitably, we were able to show that indeed we can accommodate. And it really started with Carasson who really came up with some of the main algorithms. And subsequently, we have developed it and implemented it in practice in a variety of applications. And it actually has worked very well. So here is one example. So this is a problem in a gas turbine system where there is interaction between heat that is coming from the gas that, your fuel that you're mixing with air and burning. And that basically is what the chemical energy transforms into this huge mechanical energy. And that's the one that goes into the turbine and gives you thrust. But interestingly enough, what happens is that the heat that's coming from the chemical reaction from the reactant to the product and the acoustics that are in the chamber get coupled. And when that happens, there is a huge acoustic resonance. So this is basically in red. So this is from a scaled Rolls-Royce rig, and this was in collaboration with people in the University of Cambridge. And my student went to Cambridge and implemented this thing along with all the people in Anne Dowling's lab. And the cyan color is really the pressure spectrum that you get from adaptive control. So you can see that. And again, this is totally online with no learning, no training, nothing. And you come in cold, and you're able to actually get this huge reduction compared to the baseline and compared to the nominal control because of the kind of adaptation algorithms that we were able to employ. So this is that you can see that with no information about the system, we get a significant reduction. This is an actual rig that basically produced this. Here's another example. This is simulation, but of a hypersonic vehicle. And here, we were not only worried about magnitude saturation, but we were also worried about rates, like how quickly you can actually increase this. So it turns out that if you want to really follow this particular command, you have to have a huge amount of rate, which is really not realistic. So the algorithm that we designed with all of these different kinds of processing of components basically was able to limit the rate, but still realize the performance, which is reasonable. So yes, there is some departure from the performance, but eventually you're able to follow the command. But the black is simply not realistic, and what we were able to do is to come pretty close to what we're trying to do. I think this is also one of the questions I think that I was asking you yesterday about multiple objectives. And so if you have this significant trade-off, you want to have the best of both worlds, and this basically is the one that enables you to realize that. Yet another type of constraint, which comes from safety. So not only do you want to make sure that you have the inputs subject to some constraints, but you also want the states to remain within a certain region. And how do you make sure that you can combine whatever you're trying to do in terms of performance and safety? So this is the next set of things that I want to show you. This is in collaboration with people in DLR in Germany. And so here is a very simple example. And so what you're trying to do is to start from these squares and go to the diamond, and here are the obstacles. So when you're trying to do this, and if you actually zoom in, you can see that there are some that basically, so the dashed line is your boundary, and you don't want to be, you don't want to sort of go in on the right side, but you want to be away from it. But you can see that I have some incursions there. And so we were able to then make some changes in the design and make sure that indeed you're able to stay on the correct side and reach your waypoints. So this says that you're able to reach your performance and at the same time stay safe. And so one of the things that we did was, what if you had all these other points where you were very close to the obstacle? The nice thing about the algorithm is that it's able to actually figure out the right path on its own, automated, and find its way to the waypoint without ever hitting the obstacle. So we then took this idea, and then we made it again more elaborate in terms of the quadrotor problem. And so here's again a simulation with a high fidelity, with a nonlinear model. So without any adaptation, it turns out that, oops, let me see. See, it goes and hits the obstacle on the left side, whereas with adaptation, it's able to circumvent the obstacle and reach the goal. So this is just a photorealistic simulation. Let me say here. So this is where, unfortunately, it's the obstacle. This is a room at MIT. And on the right side, with the adaptation, it's able to basically go around and reach its goal on the other side. So that's the idea behind how I mean, there's a lot of details that go into it. I'm not going into the technical details, but I just want to give you an idea of the kinds of different kinds of constraints that we look at when we look at these real-time control. And many of these concepts actually have gone into production. And these are things at Boeing where there was a number of flight tests. So everything with the ones with the star actually show the flight tests. These are all different high performance platforms. And so these are all uncrewed flight control applications where in every one of them, basically you're after improved performance and reliability. So that's that. I know it seems like a lot, but I'm going to go through them quickly. I just want to actually bring in one point about parameter learning and maybe go quickly to the last point and skip the things in the middle. So all of this has to do with performance. So the question is, what are we learning? After all, it's all about what went wrong, right? So the first thing that we do is to make sure that our foundation is safe. And then we make sure that with hindsight, we can say, OK, what happened? How did the plant actually change? So when that blade broke, what kind of, how much of it did break? Because I didn't worry about all that when I designed the controller, right? I just made sure that it hovers, it stays safe. So the idea behind learning is basically to learn the unknown parameter. So it's all about making the parameter estimate go towards the true value. So that is the learning part that we focus on in the context of adaptive control. So, and the reason why we do that is because any small change in the parameter really results in a large change in the state space. And so real-time decision is important, but beyond that, you also want to learn what went wrong, and that really contributes to robustness guarantees. So the notion of exploration is really tied intimately with what is talked about here, and with the term that we use is persistent excitation. So the persistent excitation basically says that your data spans the space of interest. So with that kind of thing, it turns out that if you have the regressor span and it toggles between these two subspaces, then you basically generate a full rank matrix as opposed to one where you don't. And it's as simple as that. And that gives you the full rank property, and that is the one in turn that gives you persistent excitation and allows you to do exploration. But if you don't have that, and remember that this is data that is coming from real-time operation of the system, you are trying to go somewhere, right? And that's, let's say, the goal. Then you don't always have excitation. You don't have the luxury of imposing exploration. That's really the challenge in adaptive control. So there is always going to be imperfect learning. And this is really the concept of dual control. Performance and learning are actually conflicting objectives. I mean, if you really want to eat good food all the time in a restaurant, and it's a new place, unknown place, you have to make some mistakes. You have to eat bad food once in a while. Unfortunate, but true. And therefore, so in order to make sure that you're able to have performance, then imperfect learning is something that you have to accommodate. And here is an example where what we're trying to do is to really always follow a certain angle of attack. But unfortunately, things change and your parameters changed. And if that happens, then you can have a big deviation in the performance. But in order to learn this, it's not always possible. So imperfect learning has to do with reaching a value which is basically in the same space, stable subspace. And so even if the parameters might be different, your performance goal is reached, right? So imperfect learning, yet stay safe performance. So that's an important thing to keep in mind. And so so this is really what we strive for in adaptation before we go to learning. And it turns out that you can actually also show that when you have imperfect learning and you try to basically continue your data continues to change, every time the data changes, there is a relearning of things that happen. And this is really what is known as bursting. And this bursting can be sometimes deleterious depending upon how safety critical your system is. Whereas with exploration, with persistent excitation, the same system actually never shows any burst because the loss function has gone to 0. And the main reason is that you fully learn. And you don't always have the luxury of making sure that this happens, though this is a better thing to have because this gives you a lot of robustness, which obviously this doesn't. So something to keep in mind. Okay. So let me maybe skip some of these things and just directly go in here. So this is one of the things where we try to bring the two things together of neural networks and adaptive control. So here we looked at a plant where the idea is that it's nonlinear. So we don't often know what the nonlinear control is. And we try to learn that using a neural network. But we used a Lyapunov-centric approach for training the weights. And that basically looked at what a candidate function that is positive definite and trying to impose a particular target and use the difference between the two as a training procedure. And with that, we were able to take a look at take a very complex nonlinear system where it's impossible to figure out what the control input should be by inspection. And it does much better compared to a linear controller, which shows that, and with analytical guarantees. And it's very similar to the kind of thing that actually Andreas has done, where there are policies which is actually 20 years later after our work, where you can indeed combine both of them together and show that when you design your training set in a way so that it intersects with the Lyapunov function level sets, you can guarantee that everything works. But this basically shows that there is a way to sort of combine the two and provide a provably correct architecture. Do I have some more time? Is that okay? Okay. So I just want to end with two examples that basically brings the whole thing a little bit closer and show you some of the ways in which you can combine an RL approach and integrate it with the real-time adaptation. So the first one in here is basically where you use RL and think of the top part in here and ignore the one at the top. Just look at the bottom. So this is basically the architecture that we developed, which is a combination of adaptive control and reinforcement learning. So the top part is the one that is based on RL. So you basically have some kind of a ground truth. And for that ground truth, which you assume is what you put in your simulation model, you come up with a policy, and this basically guarantees that the system is well behaved, right? So that's this part in here. So start with something like this. So imagine that that's the quadrotor where no propeller blades are broken, right? Okay. But now the reality is that you're dealing with not the one that you put in the simulation model, because you did not anticipate that the quadrotor needs to fly with asymmetric blades. And so that's not something that you had in your domain randomization, in which case you want your control input to figure out what to do using all of the information that you have in here. So that basically is what this loop is doing. So this is an adaptive controller which takes the policy that we derived and use that as a baseline, but then augments it with some kind of a real-time correction, which is based on an appropriately designed function, which need not be a loss function in terms of performance, but something that gives you stability. And then with that kind of a correction, this ACRL basically guarantees stability. So that's the kind of integration that we have shown, where you can leverage all of the power of RL and at the same time have that be something that supports adaptation, which you could not anticipate during the training period. So here are some of the technical details of how we actually do it. So there's a lot of complexities that go into determining this loss function that I mentioned. There are some high order tuners using Nesterov's correction and so on. So with that kind of a structure, this is the problem that we were able to address. So it's again a quadrotor. And what the quadrotor needs to do is to make sure that it lands, but the platform is also moving. So it's a challenging task compared to what I showed you earlier. And there are lots of metrics here that have specs that you have to meet, that obviously you don't want to crash. So that's that. You don't want too much variation in the XY plane. That's this. And you don't want the orientations to go out of whack, because then the model complexities basically will bring in all kinds of extraneous things that you didn't put into your design model. You don't want the velocities in the yard side slip to be too high. And of course, you don't want to come in with a huge vertical velocity, which again can lead to crash. And you want to make sure that all of this happens in 10 seconds. And so when you don't have, so here is where we introduced the loss of effectiveness. So every time the blade breaks, there is a loss of effectiveness, basically. So the increase in the percentage is basically the decrease in the moment arm, if you will. So, and if you don't really include adaptation, when you have a 50% loss of effectiveness mid-flight, if you only use RL, because the deviation from reality, the sim to real gap is very high, and so because of that, the things crash. Whereas with the adaptive controller, we are able to provide the success rate is much higher, and the success rate being defined in terms of the time it takes for it to land. And the main reason why this happens is because of the departure between what the simulation model thinks it is, which is really the red, versus the actual. Especially in the z direction, there is a significant difference, and that's the reason why the ACRL does better than the RL. The second example that I want to show you guys is about figuring out how to have an adaptation in a linear quadratic regulator. Again, there is a class of papers that have looked at it. So what we want to do is to make sure that you remain stable all the time and then move towards optimality. I just want to sort of take a step back and just, point to you guys that everything that I've talked about so far, we've talked about stability, make sure that your foundation is safe. We've talked about safety, making sure that you don't wander into regions that you're not supposed to, because the aircraft goes into stall, then that's a big bad news. You don't want that. We've talked about learning, which says that, okay, with hindsight, figure out what went wrong. So if there is persistent excitation, if there is exploration, opportunity to explore, then you can make sure that you can learn. But we didn't really talk about optimality. Whatever you're talking about is that, are you the design that you have for your controller, is it optimal? Are you using too much energy? Are you using too much control effort? Obviously, that's not desirable. So we do want to have an optimal controller. But the optimality is something very difficult to achieve when you have real-time uncertainties in a dynamic system. If something goes wrong, then you first have to make sure that your foundation is safe. So the first thing that you have to do is to control. Then the next step is then, okay, you learn what went wrong. And now that you've learned what went wrong, see if you can now pivot to an optimal controller for that degraded system. And that is really the process that you want to adopt. So that's what we're trying to do in here. So the problem is that you have a plant, and the uncertainty is in the form of your parameters A star and B star. This is linear, and then you've got your stochastic disturbances, measurement noise. And for this system, it's known that this kind of a controller actually can guarantee stabilization. But in order to design K, you need to know A star and B star, right? So this is your inner loop. So the outer loop basically then estimates what went wrong, it collects the data and comes up with a parameter estimator that designs the estimate and uses the information about that estimate to calculate the new feedback gain K. And this is really the process. Now, you collect the data, and remember, we've seen this before. This is the underlying regressor, and you want to have enough rank information in there. And so when the condition number exceeds a certain threshold is when you calculate the new feedback gain. So the question is then you investigate, has the parameter estimate improved compared to what you thought A star and B star were? And then you basically then say, yes, I do see that, and therefore you calculate. So this is the exploratory signal for learning that makes sure that you introduce some noise. It's a separate talk. I don't want to go into that. It's not always a good idea to introduce stochastic input in order to generate persistent excitation, because this is never the real plant. You always have unmodeled dynamics, and when you introduce noise, you excite those high frequencies, in which case the problem actually becomes much worse. But let's not go into that. There's a bunch of results that people have proposed in the literature, and so what needs to happen in order for this to work is that the initial controller needs to be stabilizing. And so because you need to collect the data for a while. And the problem is that what do you do if the initial controller is not stabilizing? Then you need a lot of excitation to learn quickly and stabilize. So in order to really address these problems of stability relying on excitation initial controller and requires difficult optimization, we develop an algorithm that does not require any of them. And here, what we do is to use a direct approach. And the direct approach basically has these gains, KT and GT, And what this allows you to do is instead of estimating the plant parameters, you directly estimate the control parameters. And that information then is used in order to calculate the new ground truth, which is sort of a better model of the degraded system, if you will. And then you use that in order to really control the system. So when we looked at this example, we were able to show that our algorithm with the Gaussian noise exploration is the orange one, and it does much better. It's more optimal, and the magnitude stays smaller. And when we took that same approach and we explored the 6-DOF quadrotor, once again, our algorithm resulted in a more optimal thing in terms of regret. And the pitch angle stayed smaller, which is a good thing in terms of meeting the constraints. So that really is what I wanted to share with you. I hope I've been able to give you an idea of how adaptive control looks at classes of problems where many of the tools are very similar, and we are able to actually exploit the synergy between AC and RL, given that RL has a very structured and powerful way of dealing with collecting information offline and figuring out ways of optimizing things when you have a very unstructured cost function. And we were able to leverage those things and combine the two, and that's what we were able to do in both of these examples. So the kinds of things that we're working on right now is to really move towards ways in which you can have inner loop decisions with outer loop kind of management of where you want to be, so that we can anticipate what needs. So these are control barrier functions that give you a way of staying within a certain bound so that you don't have the propensity to violate some important state constraints. So how do you make sure that all of these things happen? And even while you're designing the inner loop, can we take this whole triumvirate of control, learning, and optimality and squeeze that time frame so that you can do everything fairly quickly and you become optimal as quickly as possible, even in the presence of uncertainties. So the takeaways here are that when you're trying to do real-time control, adaptation becomes important. You don't always have the luxury of making sure that there is exploration. And so guarantees with imperfect learning becomes essential in a safety-critical system, and learning comes with hindsight. And so in order to design fully autonomous system, which is the holy grail in many engineering problems, we really need these real-time decision-making tools where there's integration with a lot of building blocks, including RL and other outer loop designs. So in many of these things, it's not always learning for control, and sometimes it is control for learning, and that needs to be addressed, especially when you're trying to do decision-making under fast timescales. Here are some publications. Thank you very much.
Yeah, thank you. Really nice talk. So I was wondering, a lot of the example was on this quad that suddenly kind of a blade fall off, right?
Sorry, say that again.
So the examples that you showed were based on this quad where suddenly a blade fall off, right? So it seems to me that this is like a discrete change, right?
Yeah.
But the analysis that you presented, except for the last part, is based on the Lyapunov functions and continuous kind of continuity and equilibria and so on, which is a local notion. So in a way, from an outsider's perspective, I see kind of a gap between the mathematical tool and the problem that you look at. Do you think is there some potential for switching or so on?
Right. So the quadrotor demonstration that I showed you is hardware, which is for the real system. The design was based on a linear model. But we always end up, but all of the examples that I showed you, that it's always in the context of evaluation of the real model where you're far from the equilibrium, there are all kinds of nonlinearities and so on. So the idea behind the theory, the Lyapunov function, is to say not only that everything is stable and converges to zero, but there is always robustness. And so we make sure that even when there are departures, and that's the reason why I showed one slide on robustness, there are other kinds of anomalies that are not always something that we can accommodate, but the intrinsic control design has a certain amount of robustness, and that basically is why it works even for these more complex systems. So we always keep that gap in mind implicitly when we look at these designs, because all of them come with a certain amount of inherent robustness. Now, I didn't go into that in the slides in here, but we've looked at a hypersonic vehicle, which basically has to switch between several equilibrium points. During one single flight envelope, that's what it has to traverse. So what we do in that case is basically to study what the equilibrium points are that it traverses. So then essentially you have a whole bunch of piecewise linear type of things, and so you gain schedule, and then you switch between these different models. So all of your reference models is not just one, but a bank of them, and your algorithm basically accommodates that switching, and and that's how you proceed. So there are all these other sort of tools in our toolkit which we deploy in a very concerted manner so that we are aware of all of the different gaps that we need to fulfill in a given problem. That doesn't mean that there's so many problems that we've just scratched the surface. Like I told you, I can talk about this topic for days, and I would still have only scratched the surface of what we have done and how much more remains. So in the example that I showed you, sorry about the long answer here, there are certain structures that we assume that we know. The underlying regressors, for instance, need to be known in order for adaptive control to work, which means that there is a certain amount of physical information that I know. I know I'm dealing with an airplane. I know, therefore, these are the regressors. In a power system, we have quadratic nonlinearities. Here, you basically have saturation nonlinearity. So you know information about the kinds of underlying regressors that you have, which you leverage. Doesn't mean that you always know those regressors. So that's where I think an integration and a marriage between RL can really help, because RL might give you an opportunity to learn some of those regressors offline. So there's so much more to be done. Thank you.
Yeah, maybe thank you for the talk. I have a quick question. I guess if you are designing your adaptive control, that is for one type of anomaly, right? If you now have different type of anomalies that you want to attack, how do you prevent these adaptive control to interfere?
Yeah. So in the example that I showed you with where it navigated the pillars, we assumed there were two propeller blades that broke, if you will. And we've deliberately made it asymmetric. But we didn't know what they were. We didn't know that those two would break, or any of those could have broken, and the adaptation would still work. So, however, I mean, if it breaks so much that you lose control altogether, then it's like controllability is a necessary condition. So it breaks so much, but not so much that you can't even, that you die. So in that case, nobody can do anything. So there is a certain amount of generality in this. So we don't use any kind of information about which propeller blade broke or anything in the design. So there is some level of agnosticism that is inbuilt into the design. That doesn't mean that we can, so there are large classes of parametric uncertainties that this is designed to handle. But if there are, it's hard for me to come up with a counterexample, but there are some that you can envision, in which case whatever I'm proposing will not work. But in terms of different kinds of degrees of propeller blades breaking, no problem. That's a cakewalk. I don't know if I answered your question or not. But we can talk more during coffee break or something and figure out what that would be.